Hello, everyone, and a very warm welcome to Kognito Key. I am absolutely thrilled to have you here today. If you've ever looked at a rushing river or felt a sudden gust of wind and thought, how on earth do we actually measure the speed of something so invisible and fast-moving? Well, you are in the exact right place. Today's explainer is all about a truly brilliant piece of engineering called the Hot Wire Anemometer. Let's be real, fluid mechanics can be notoriously tricky. Trying to measure a moving fluid stream without completely disrupting its natural flow, that is a massive headache for engineers. I mean, you can't exactly stick a giant mechanical ruler into a jet engine's airflow and expect to get accurate results, right? So science had to get creative, and they came up with a really clever heat-based solution. Okay, so let's get right into it. At its core, a hot wire anemometer is just a device used to measure the velocity and the direction of a fluid. But how does it actually do that? Well, it measures the heat loss of an electrically heated wire placed directly into that fluid stream. So instead of measuring the fluid mechanically, we're actually measuring it thermally. It's kind of mind-blowing when you think about it. And this whole concept brilliantly illustrates the fundamental physics at play here. It's the golden rule of thermodynamics. Heat is always going to transfer from a high temperature to a low temperature. You can think of it almost like a conversation between the instrument and its environment. We place this really hot, glowing wire into a cool, rushing liquid or gas. As the fluid rushes past the wire, it literally steals its heat. And naturally, the faster the fluid moves, the more heat it takes away. Let's look at the physical construction, the actual anatomy of this instrument, because it's surprisingly elegant. It really just consists of two main parts. First up, we have the conducting wire itself, which is safely housed inside a little ceramic body just to give it some structure. From there, the wires are taken out of the ceramic housing and connected directly to a Wheatstone bridge. Now, if you remember your basic electronics, a Wheatstone bridge is absolutely fantastic for measuring even the tiniest microscopic variations in electrical resistance. So now that we have our instrument built, there are actually two distinct ways we can operate it. We've got the constant current method and the constant temperature method. Both of these rely heavily on that Wheatstone bridge we just talked about, but they balance the system in completely opposite ways to give us our final flow rate. Let's break them down one by one. First up is the constant current method. Imagine we place our anemometer into the fluid stream. Step 1, we pass a current of a very constant magnitude straight through the wire, while keeping the Wheatstone bridge at a constant voltage too. Step 2, as the fluid flows by, it transfers heat away from our wire. Now for step 3. Because heat is directly proportional to the resistance of the wire, as the wire cools down, its resistance drops as well. Finally, the Wheatstone bridge measures that exact variation in resistance. And bingo, that resistance variation perfectly equals the flow rate of the liquid. This brings us to a really crucial point perfectly captured in our source material regarding the second method. It says, the total current required to bring the wire in the initial condition is equal to the flow rate of the gas. Notice how the logic completely flips here? Instead of just sitting back and watching the resistance drop, we're actively fighting the cooling effect to keep everything exactly the same. Let's see how that plays out. So this is the constant temperature method. Just like before, the hot wire transfers heat to the moving fluid, and naturally the wire's temperature and resistance begin to drop. But here is the absolute genius part. The system instantly injects the exact amount of electric current needed to bring that wire's temperature right back up to its starting point. The temperature stays perfectly constant, the bridge remains totally balanced, and we figure out the fluid's speed simply by measuring how much extra heating current we had to actively feed the wire to fight off that cooling fluid. Of course, getting precise measurements means we have to do a little bit of math. The heat loss from our heated wire is determined by the fluid's velocity, that's V, and its density, ρ, alongside a couple of specific constants, A and B, which are just based on the wire's physical dimensions. To keep track of our crucial electrical current I and resistance R, a standard resistor is connected in series, and a potentiometer steps in to help us pinpoint the exact voltage drop. It sounds complex, but it's basically just keeping tabs on the electricity. And that brings us to the beautiful climax of this whole technical breakdown. In equilibrium condition, heat generated equals heat lost. By keeping the resistance and temperature of the instrument completely constant, we just let the physics do all the hard work for us. We can instantly know the exact velocity of the rushing fluid simply by measuring the current, I, that we are feeding into the system. It's such a stunning example of converting a tricky mechanical problem into a super elegant electrical solution. So, I want to leave you with this final thought. Every single fluid stream, no matter how invisible or chaotic it might seem, leaves a thermal footprint. By understanding how heat transfers, we can literally map out the unseen currents of the world around us. Thank you so much for joining me today on Kognito Key. If you found this visual explainer of the hot wire anemometer helpful, please hit that subscribe button, give this explainer a like, and share it with your fellow engineering enthusiasts. Until next time, keep learning and stay curious.